Attending. So good morning, good afternoon, wherever you are, and welcome to this TDL webinar on the highly relevant subject of AI, energy consumption, and sustainability. We have an excellent panel. This will be recorded. This is being recorded, and a recording will be made available shortly afterwards, as will a short summary report. And with that, I'd like to hand over to our TDL Strategic Advisor, Claire Bishik, who will lead us through the next hour and moderate our session. Over to you, Claire.
Thank you very much, David, and thank you to Trust in Digital Life for organizing and hosting this series of events. We read a lot about artificial intelligence, how it transformed the way we do a lot of things, how it ramped up the activity in data centers, how it created new architectures and new designs for components, how it is going to change the world. We are also reading a lot about other resource-intensive areas, such as cryptography, including privacy-supporting technologies such as homomorphic encryption. They also require a lot of cycles in order to operate. And we read some economic analysis of what is happening. Recently, I read that because of the costs, including energy consumption, it is now maybe more expensive to extend AI availability for additional systems and use cases than hire people to do similar work. This in itself, even if true, is not surprising. Where automation started, it always has been the case that the early adoption was expensive for a variety of reasons. Some of us here are old enough to remember the dearth of bandwidth. I joined AT&T Labs in 2000, and that's where we were developing in the first years a number of applications, approaches, and algorithms that were essentially bandwidth saving. Now bandwidth is plentiful. No one is complaining about building specific applications to use minimal possible bandwidth. And probably the same will happen to the current resource intensive, energy intensive applications, but this is still ahead of us. We have some approaches, but we don't have solutions, in part because once we gain efficiency, there is immediately more demand. And we do gain efficiency in all areas, in energy efficient encryption, in advanced cooling, in creating components that are more energy efficient substantially than what was created before. But still, the growth in demand consumes this relatively modest at this time efficiency improvements. So where do we stand now? What is going to happen in the near future? What are the important areas where we need to focus? All this we are going to discuss today. And we will start with talking about the space at large. What do you think is happening? What do you think are the most important developments? What do you think are the developments that will not help very much? What do you think is really important in the area of energy efficiency and sustainability in computing? I will ask our great participants to answer these questions. We have today 4 distinguished panelists, and I am sure they will provide incredible insights into this problem. We have Ro Camarota, who is associate professor at UC Irvine. Um, he is chief scientist advisor leader and in encrypted computing and in privacy preserving AI, a very important area. We have Sean Coe, who is senior director of tech leadership um, and communities at Intel Labs, who just retired from this job. We have Rahima Mohammad, semiconductor technical advisor at Vinci 4D AI. And finally, we have Marcus Pan, who is chair of AI and mixed signal hardware track in IEEE Design Automation Conference, DAC. With that, uh, let us start this discussion. And for the first question, to provide your general overview of the space, I will start in the alphabetical order of the last names. Ro, what do you think is happening? What do you think is important?
Yeah, thanks, Claire. Thanks everyone for having me. I think the problem of AI energy consumption is definitely a big one. This is the fourth probably industrial revolution, and typically I look at it from the lens of a technologist. But if we do that, we would systematically underestimate the problem for as big as it is. And so what I see is sustainability is key, and it has various components. Grossly, I would bucket them in three. So there are three dynamics at play. So the first is that there is infrastructure constraint. We are doing AI now, and AI is changing at a pace that is a lot faster than the infrastructure and what we are building typically catches up. Then there is something, this is a little bit controversial, say it like this, but software model inefficiency. So typically I would start talking about framework for AI, how to put privacy, but really it's a product management choice, is how you define the product and how do you make the product actually being efficient and being cut for the specific purpose. And most importantly, there is a explosive demand that will continue being because AI is different in many ways from anything that we have seen before in terms of automation because it becomes an expansion of what we do. And that makes a huge difference. So what I believe is that the key question is that when we ask ourselves, can we make AI more efficient? And yes, that's one question. But the point is that can we align incentives across the stack such that the growth demand doesn't outpace the technology development, and that will lead us to sustainability. And so the solution space combines three elements, more efficient hardware and model, smarter operational strategies, so how to deploy it properly, and governance mechanisms. Governance give trust into technology, right? If we are sure that we are not deploying AI and consuming all the resources on Earth and extended Earth in the universe and things like that, then maybe we are more willing to use it. And so without a systematic view of all of these, I believe we risk to optimize things locally, right? While the total energy footprint continue to expand, and that's definitely not a sustainable solution.
That's an excellent overview of the three areas that you outlined. Do you see one of them as the most important, or are all three equally important?
Well, they come with different timelines. They are all three equally important. I'm of the, I like to think that everything is important and so nothing has priority, but actually the life cycle of the tree is very, very different. So the operational strategies, like for example, allocating more smartly and more securely workload on the infrastructure that we have is something that can be done today. Um, the hardware and models and things, they also have, so the models efficiency can be done today. The hardware cycles are fairly longer, okay? And governance mechanisms are typically things that run through the various consortiums, global consortiums that we typically participate to build the standards and policies and things, they have yet a longer timeline. Changing infrastructure fundamentally, because that is invasive into whatever it is, the smart cities and things like that, it's also something that have longer cycles. If I have to prioritize based on this, I would say that operationally we can do better. Model will continue improving, but they need to be more customized. Then it comes the hardware, then it comes the governments that oversees all of this. And slowly it will change the way the environment around us with which we interact now with the AI is going to look like, and hopefully it's going to be sustainable.
Thank you. So do you think it will be a process similar to what happened with bandwidth? First, there will be new architectures, efficiency technologies, then there will be infrastructure improvement and new standards, and finally, there will be relative abundance where different things matter. Or do you think some other paths will be taken?
No, I think there is similarity into all of this. It's just that the scale of the problem is um, meaningfully larger than what bandwidth is, just because of how AI is like an octopus. It just gets the tentacles pretty much into anything that you may think of, and it impacts directly people. Whereas bandwidth, we needed to be creative on how to use it, right? And then convince
Um,
people to adopt it. People are convinced that AI is coming. You know, there are the optimists, there are the gloomers. I'm on the optimist side, right? But it's just a problem of scale. And when it comes to scale, it's not necessarily obvious that we know how to harness it. That's why governance is very important.
yeah, it's amazing that you use this term decades ago already. I remember a prominent scientist in a panel saying that bandwidth is like an octopus. We need it to reach every home. So octopus, I guess, is a metaphor that continues to be relevant always, at least during the last several decades. Thank you very much, Ro. Let's continue. Sean, what do you think is important? What do you think is going to happen?
Yeah, well, I think I spend a lot of time working often with many of you looking for disruptors, technology disruptors, things would really change the game. And I think we're living through one of the biggest disruptions that I've ever seen in my life, and maybe that the world has ever seen in some sense. I mean, this sort of capability that's come on with AI and LLMs is something I think that has happened to a greater degree than anyone expected. And I think what's happened along with it now, we've seen like over $1 trillion invested in that potential. And it's sort of compounding the effect. There's an excitement around it, but then there's also an investment that needs to see a return. So I think we're seeing across the board just an exuberance in the industry and in governments to try to push adoption of AI across many fields. It's happening very fast. And I remember talking with some of my colleagues that were kind of working on the model side, like Gadi Singer. I think when they build these foundation models, they're meant to be like a concept car. They're gigantic. They're huge, trillion parameter models. And it's almost like we're all trying to go sell the concept car, which is the most expensive least efficient way you can build something. So I think there's going to have to be innovation in the models, to Rose's point, to create more specialized, energy efficient, much smaller models. But I think what we're seeing because of this exuberance is just innovation across the board to address the demand, from the architecture side, but also energy efficiency. And it's challenging and it's creating, I think, a lot of stress on the system. A lot of these things don't move very fast, as Rose said. Just in preparation for this, I spoke to a colleague, Mike Whitteman, former Intel colleague. He works for a company called Virtue Tech that works with climate startups. And one silver lining is they're seeing a receptivity to innovation in the grid right now that they've never seen before. They've always been trying to push innovation in the grid, and everyone's always, in theory, wanted to do that. But now they really have to because these data centers are getting built right now. And unfortunately, though, it takes them normally several years to incorporate things like green technology, like wind and solar, into the grid. So they're even looking at things like digital twin technologies, so you can simulate how the architecture, the system is going to change, so they can incorporate these more green technologies in faster. But of course, they're not necessarily to lower energy consumption. They're now to meet the demands of the AI data centers, which is kind of that Jevons paradox you mentioned. So I think there's attempts to across the stack at every layer to try to make things more efficient, but ultimately I think it's that concept car. It's like these models are like way bigger than they need to be, and if you want to get like not just incremental gains, but dramatic like 10 or 100 or 1000x gains, I think it's going to be at the model layer that the innovation needs to happen.
Thank you. And this is a very good way to describe the situation. I certainly heard it in other venues and read it in papers. There is a lot of interest these days in AI agents. Agents may be technologically different. They provide for a different pairing, for instance, of CPUs and GPUs, or TPUs, where it's almost parity among them. Do you think approaches such as agents will improve the situation, or will escalate it further because of the number of possible agents that can be created?
Well, I can't see that reducing the compute demand. I mean, that's just another layer of, I think, activity, and there I think the agents will be drawing upon the LLMs in kind of another layer of compute built on top of it. But it could, like I said, just the mentality of shifting to kind of a more personalized approach, might lead to models that can be run for an individual's needs, that may not need to be a trillion parameters, that may be able to run on a local system, or not need to necessarily run on one of these massive data centers. So it could shift some of the balance of compute to these more specialized tasks that then may be offloading the larger compute. So maybe there's a path to that as well.
Very interesting. And one of the thoughts you presented here, that we need a radical grid improvement. We will return to it in the next topic of our discussion, but it's a very interesting field, very interesting subject that could lead to significant innovation that will truly change the world, not just for AI. Thank you very much, Sean. Rahima, you are looking at some practical ways to deal with the energy situation in AI and other energy intensive applications of computing. What do you see? How would you describe this situation?
Yeah, thank you, Claire. And thanks to both Ro and Sean for their very good, eloquent explanations. So actually, in my case, I come from a slightly different layer. I spent about 27 years at Intel, most recently as a senior principal engineer, leading actually thermal and validation work before joining Vinci 4D earlier this year. And now I think this actually shapes the view slightly differently, because in this case, my concerns are much more looking into 600 watts per centimeter square, to how that meets a real package, a real cooling architecture, and a real grid, because those are the aspects that you have to think through. So the number that kind of anchors in my mind is this growth of 948 terawatts. That's kind of the IEA projection of the global data center electricity by 2030. And it's moving from the 400s to 948. So that's actually equivalent to Japan's entire consumption today. Can you imagine that? So today, and then one of the other trends that we have seen is the per rack power has actually gone from 30 kilowatts to 140 kilowatts in just 3 generations. So in only 3 generations, it has gone that high. So the binding constraint is no longer only compute or algorithms, but it's actually the heat, the package, and kind of the grid economics that flow from that. Because how do you all the way to the end? And Sean made a very good point of how long it takes. Before, it used to be a 20-month cycle. Now it's inevitable. Getting access to the grid is a 5-year cycle. And if you look at the queue, there are some that are in the 7 to 12 years. So there has to be something completely different to be done about this. So in my case, for the energy efficiency, I'm thinking of it in, or I would like to put the framework as a 4-layered stack. And the layer 1 is where the heat gets generated. And that is where the component and the package comes in. And the layer 2 is actually where the silicon design and the validation, where efficiency is locked in. So you want to, this is the SKU, this is the details that we are going to go through. Layer 3 is actually the system and the data center deployment, where truly the physics meets the reality. Okay. Layer 4 is the AI ML applied to the engineering itself, and that's truly the meta layer. What can we do across all these 4 layers is what we should be discussing. And most of the industry, if you look at just nowadays, because I'm at Vinci, I take a look at a lot of startups as well as, of course, the big ones. So if you take a good look at the lay of the land, there's a lot of new startups coming at each of these layers. But I think what's very exciting, or will really get to us a solution, is when we can truly look at none of it is in one single layer, but across the layers, and how do we kind of bring all of that together and bring that collaboration together will actually help us to get there. So that's my thinking. And of course, I would love to talk about the different layers and what are the innovations happening across and how we can bring it all together.
Yeah, that's a very well articulated vision that highlights how difficult it will be to change the situation. If you look at all the layers you mentioned, which one you would say is the greatest bottleneck, the greatest challenge that we have today, and why?
The fundamental challenge is, of course, the amount of heat you're producing. So you could be taking this thing just a cooling problem, but it's not. It's a cooling problem. I think there's a lot of work that's being done in the microfluidics. And I'm sure you guys probably know very well the number of new processors that you have, whether CPU, GPU, TPU, the ASICs, and name it, there's just a lot of them, right? But the workload scheduling seems to be a very big one today, because you have to think about solutions that you can do today. That is an area, and I think that is very connected to what Sean talked about, which is the digital twin. Because if you can do a very good digital twin, then you can actually do the workload scheduling. But I think the very fundamental one that needs a lot of work is the power, flexibility, and the grid. And there is another version of which is coming up very much, and almost at least a plethora of companies are working into. This is the co-packaged optics, the near packaged optics, and the linear packaged optics, or everything related to photonics. And then there's only a few companies which are actually taking a very good look at the holistically across the layers, like Majestic AI. They are Majestic Labs, I think they're called. They are looking at it more from a holistic perspective. Now, in order to achieve all of this, one of the fundamental layers that we have to attack is simulations at the manufacturing resolution to the detail level, because you don't have time. Time to market is everything. And you don't have time to do the amount of actual validation that you need to do, because you have to really move everything to simulation. So that's kind of the strategy of the 7 things that I've been looking into.
Thank you. Yeah, it looks like the complexity, based on what you said, will only increase short term, considering the cycles, considering the necessary investment in the grid, considering the speed that the investment in data centers needs to be realized, and all of those other areas that you described. Well, we will discuss it further. Now, Marcus, what is your view of the field? What do you think is happening? What do you think will happen?
Yeah, and thanks for inviting me to this panel. I've seen all the great innovators online, right? And I want to echo Soshan, and especially on the digital twins innovations, on the AI workload, right? I think that if you take a look at the power grids that people are using nowadays, it was sort of established decades ago. 99% of the time, we are over designing the power grid. It doesn't changing with the AI workload. I think in a very near future, to mitigate all the power problems, we need digital twins, especially the standards, right, to highlight and predict the AI workload and shift the workload to the from one data center to others, accordingly also shift the power accordingly. So I see several startup companies working in that domains, and I do see that the policy from the government to mandate that the requirements for all the big data centers will be helpful. So that's the first one. I think is to Sean's point. And second point to Rahim's and also Ross' point. I think for the full stack optimizations, we optimize everything, right? All the way from button, device, circuit systems, algorithm, and so on. One of the things we see, especially from the public-private partnership, is that the efficiency and versus inefficiency. People all think efficiency is important, but you take a look at the benchmark for each application. We talk about the AI streaming or the AI chatbot, right? There's not enough scorecard or benchmark to highlight the inefficiency. So think about the AI hardware is like the engine of the industrial revolution cited by Jason Huang before, right? So we have to highlight the inefficiency versus efficiency with benchmark of cross-stack and for each application, so people can choose the best one to use. Similar to what you when you choose a car to buy, right? It's similar to the miles per gallon. You'll choose the best one to use, right? So we can avoid the inefficiency usage in all kinds of major applications. So I just want to have two lights and want to thanks all the panelists to bring out the great points before me.
Those are excellent points. And moving on in our discussion, where do you think lie the most realistic mitigations? It is very true that providing the right benchmarks, visibility into the efficiency space will inform the users and may potentially change the markets. But those parameters, similarly to privacy, for instance, are very difficult to separate from externalities, and they do not frequently, they do sometimes, but they do not frequently inform the movement of the markets. So something more market-oriented probably is needed in order to really shift the thinking from this, oh, we gained a little bit of efficiency and now we can provide more features, to something like we gained a little bit of efficiency, but that's not enough. We need to continue gaining it because that's essential. What do you think are the most realistic mitigations in the short term?
Yeah, I think it's Claire, you're absolutely right. I think the market changing so rapidly, as Sean and Ron mentioned, right? The parameter for models change every 6 months or 3 months, right? So fast that I think that by the end of days, it will go to the. I think so. I'll start with the power regulation first, because all the power factory nowadays is super old. right? So they're the first one has to respond. If you have a super large workload and you sign a contract with those giant tech companies like Google and Meta and so on, what would you do with those AI workload? And starting that along with the nonprofit organization like IEEE, we can develop a very high level standard and try to regulate from the top to bottom. It's difficult to start for all the device to the application side, but I think from the top to down in the near term will be a little bit easier, to your point.
Yeah, I agree. I think that is true. Karima, do you want to mention, Rahima, do you want to say something
No, I'm good.
on the subject?
No, I'm good.
Okay, then let's continue the discussion. Sean, what do you think are, in your opinion, the most realistic mitigations
Well,
in
I
the short
mean,
term? What do you think?
like I said, the models do change on a week by week basis, so that's where things can happen the quickest. Things move slower in hardware, but for the things in hardware, I mean, some of the interesting things I've seen in the last few years that are not as long term. Some of those power regulation technologies. We're working on some new materials like gallium nitride, which are a little bit more efficient at power delivery. That we're starting to, bring from, non-computer applications like in industry into kind of electronics that could help. There's techniques I've seen like for power delivery, like voltage stacking, where you lose a lot of power transforming the voltage from like 54 volts down to the very low voltage of a chip, because you're trying to push those voltages lower and lower. So you can wire them up in series. So the voltages kind of drops stage by stage, but then you have to have a very even workload. But fortunately, AI is a very even workload. It's kind of very highly parallelized, so that's conducive to that. Um, that one of the challenges though is we've been trying to push down voltages at the technology or transistor level, and we're starting to hit. It's starting to get very challenging to lower the voltages, so that you have to sort of move things up the stack into the system and try to take care of them at higher levels. One other one, we've talked about cooling, right? And fluidics can help, and then there's immersion cooling, where you dunk the entire server system, server rack in basically a bathtub of some non-conductive liquid. And that, I think, is just a matter of qualifying the parts, right, to work in that immersed environment. And most of them work pretty well, but they get worried about things like warranties. Are they going to fail? Because we've never run things under under a liquid for that long. But then you can extract the heat, and you can actually transport the heat somewhere to use it usefully somewhere else. If your data center is near a town, you can pull that heat out and use it to heat things. So it's a little bit there's kind of a benefit there. So those are some of the things I've seen that I think are interesting. That are sort of maybe midterm technologies.
Yeah, it's a very good list. You said a few words about materials. It certainly is not yet the time for high temperature superconductors, even though redesigning computing in the grid with those materials, if they were commercially viable, would be great. What kind of materials do you think will be conducive to immediate progress if they are used?
Well, I mean, there's the gallium nitride I mentioned. There's with heat spreaders. I remember we worked with some teams that were looking at pulling in some technologies from NASA that they use, in space technology to very efficiently diamond-based, for instance, heat spreaders that can much more efficiently pull heat out. And that's not particularly near term. I have some thoughts on longer term technologies, but maybe that's for a later part of the discussion.
Right. Thank you. Thank you very much. That's excellent. Rob, what do you see as immediate mitigations that are available in both AI and crypto support in terms of energy efficiency?
Let's start with AI, then we get on the crypto side, okay? So I think you mentioned about agentic AI and heterogeneity. Okay, I want to follow up on these 2 points. So first of all, there is a very key distinction when we talk about AI. We typically, or at least the majority of the discussion, leads people to think that you are training larger and larger and larger models, and that is true. But actually, what we are really talking here is that the models are deployed and they are used 24/7 for inferring things. So we are talking about inference. From that perspective, I think the operational optimization, this is a case where, let me say this, diversity, comes to play again to help us. So the fact that an inference pipeline for agent enjoys a very diversified pool of hardware is a good thing. Okay, because that itself allows to build models to optimally schedule things in an energy aware things. So diversity gives that hook for which at least you have some theoretical bound on how much energy you can actually use for a certain set of model. So I think the scheduling that has emerged, among the operational optimization, the scheduling that emerged across the panelists is something that gives immediate benefits. And now that needs to clash basically with the details of, how the framework for AIs are built, what are the various requirements in terms of, I'm an advocate for private AI. So to me, it's not only about AI, it's about we need trust. Information needs to be protected because unintended consequence of computation may leak information, even if the system is completely trusted and not under attack. So from that perspective, beyond the operational aspect of it and creative solutions, like Sean was saying earlier, that this new infrastructure we produce out of it that you can harvest and use differently. I think that's actually a very interesting angle. When you start introducing beyond the scope of AI trustworthiness and things, you need to go a little bit below the level of algorithmics and orchestration and start thinking to solutions that bring new devices. To Rashma's point, there are two trends. So first, it seems that this is not the time to slow down Moore's law. Actually, the ex-president and CEO of IMEC last week at the DATE conference was very clear about it. He is saying we will make technology continue scaling. That was the first thing. And the other advantage in energy efficiency, and that will give you the next envelope of energy efficiency and performance. And the other part of it is what Rashma was saying, which is basically in-package and off-package silicon photonics. Now, when you put into it protections like cryptography for AI, you get to the next level of energy efficiency problem because typically cryptography gives you an activity factor that is 3x. And in all these new elements for trustworthiness that you are bringing within the system, namely encrypted computation, maybe side channel resistant for AI because there's still an IP problem, and post quantum cryptography, there are three themes that are constantly occurring. So the first, you need a new hardware block because you need to go to the next level of energy efficiency. And so all of them need new security primitives. The second is software defined. So what does that mean? That this hardware needs to be purposely smaller and smaller, but very, very simple, which is kind of going on a different route from what we are used to design hardware today. And I have to say that simplicity in the hardware design is that we are learning from things like building hardware for homomorphic encryption, which is something that I've been busy doing for the past 5 years. Right, has some similarity with the way actually ASIC and purpose hardware is being developed for artificial intelligence. And the reason for that, similarly to cryptographic driven workloads, artificial intelligence workloads are somewhat less dynamic when you look at the inference case than ordinary workloads, where you actually can say that. And the dynamism mostly comes because the frameworks are built into a certain way, not because the algorithm itself is dynamic. And that gives us another angle to shift basically the attention to simplify the way we do hardware, right? And move things toward the software definition that is more flexible and faster to adapt. So from that perspective, I think the orchestration is definitely the first thing, right, as a mitigation. Trustworthiness needs to be put in that, like new form of encryption, encrypted data processing, but that will come with the new ASIC elements, right? But altogether, it gives you a diversity of hardware to target, which allows you to build models for optimal energy efficiency. And now, of course, if product definition is such that there is a buy-in to build models that are more purposely built for certain tasks, and those are accepted and deployed, then it becomes easier to do all this orchestration and things because the whole problem is less of a scale than I mentioned earlier.
Thank you, Ro. That is a great answer. Diversity in the computing environment has always been a holy grail, at least in my memory, for a variety of reasons. But it has never been truly achieved for mostly economic and scalability reasons. A new area becomes a sort of harbinger of diversity, and then in a few years or maybe a decade, it becomes dominant and the diversity declines again. Why do you think it will be different this time?
That's a very good question. This is a very similar question related to when you do new technology, you need the time to develop it. By the time you have done, it's obsolete. It's a very similar kind of question. No, I think so first of all, we are not alien to diversity in the semiconductor industry. And so let me draw a little bit of a parallel here. The mobile industry. I was at Qualcomm before being at Intel, before being a professor at UCI. At Qualcomm, you used to build in that pocket of the semiconductor industry, you used to build very heterogeneous systems. So that has percolated in within companies that are more used to target less mobile devices, more data center type of things. That's percolated very, very late. In the way you design the system and the way even you think to systems. Okay, but now with artificial intelligence, that's inevitable. It is absolutely inevitable. Because otherwise, all the metrics that Rahima was telling us, you cannot reason about them without heterogeneity. It's absolutely impossible to do that. And now there was another point that also emerged across the panelists, and I think it's crucial, which is okay, we need to know things before we actually do, right? Which introduces the thing of digital twins, so which also the US government has been very sensitive about it from probably very, 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 very early stages, as Marcus was saying earlier. I think, yes, we do need simulation at scale to start reasoning about it. The devil will always be in the detail at the end of the day. But if you start with some confidence that at least you can rule out things, not that you go straight to the right thing, but you prune the space of possibility, it's probably better. So I think heterogeneity is inevitable for sustainability.
Thank you. I want to believe that diversity and heterogeneity are inevitable. We will need to revisit the subject in 5 years to assess the direction of industry so far. But excellent points. Rahima, what do you think are the economic drivers that you observe in your space? How could they lead to maybe additional diversity, additional consolidation, introduction of new approaches? What do you think will happen?
So thank you. I think that you can hear me, right?
Yes.
Can you? Okay. So I think very interestingly, I'll touch on something that Ro just talked about, and I'll add to what you're saying. So it's very interesting because in many cases, when we are thinking about the simulation at scale, and you need the simulation at scale at all the levels. And just give you one example. On the AI workloads, for example, we know that it is pretty high almost all the time. But there are instances when it is 50% higher there are instances, it's like at the microsecond level. And then you have instances where, actually I said that wrong. The 50% is around tens of milliseconds. And 100% is like in the order of 1 millisecond. As soon as you get to the microsecond, then you can even go to 300% higher. All of this has an impact on the reliability of the product. So how long can you sustain it at these levels? And the validation or simulation at scale, the details that you have to think about is at all the way from microseconds to the duration of the whole workload. And when you're thinking of the whole digital twin, how many times, so it's not only the burst, it's not only the duration, but also the frequency at which it's happening. So simulation at scale includes the transients, the steady, and at every physics. So the physics intelligence of how you achieve this becomes a very critical factor. So that's from the simulation at scale discussion. I think Marcus was talking about workload scheduling and kind of coming up with some of the how we measure efficiency and inefficiency. I think that is a very interesting point because when you're thinking of workload scheduling, we have to think very carefully about not only the current ones like PUE, the power usage effectiveness, but much more. Are you carbon aware? Are you thermal aware? And the inefficiency and the efficiency has to be thinking through across all the layers. And I think today we actually don't have a very good mechanism for that. So I think as many of us are coming together for this type of discussions, even coming up with the right metrics to kind of achieve these goals may help us to kind of measure ourselves from now, immediately, and in the long term. So I think that's kind of the effectiveness. So I think you had another question. Remind me the question.
I think what you said is very interesting. I get these questions in different discussions frequently. For instance, what is the main signal that would tell you that you are making progress in energy efficiency? And just like you said, there is no one signal that you can rely on because this consolidated view, coherent view of the space has not been developed. And I think it's very important for those planning, simulation, and developing new areas of research. Now, talking about our metaphor of bandwidth, again, back in the day, a lot of research that I have done that was already 25, 26 years ago was how can you create algorithms that eliminate peaks and valleys in video transfer so you could use the most efficiently the available bandwidth. So what you talked about was somewhat similar, right? How can you simulate the greater efficiency using digital twins Well, again, do you think this line of work will be ultimately invalidated by abundance, or do you think it will remain relevant?
In my mind, it'll be made more relevant. And why this would be so critical is because today our methodologies or our simulation capabilities are not as developed. We are not getting down to the manufacturing resolution level as we need to. So if you get down to that, because we don't have that capability, what we are actually doing now is when we design, we are always designing, putting some additional guard band. So if you look at it, when we are coming up with the details of the cooling, details of the power delivery, we have a safety factor of 25%, 20 to 25%, in certain cases, even 30%. So you can kind of as the simulation capabilities, simulation at scale capabilities, the digital twin capabilities truly become to that level where you can trace where are the peaks and valleys of your workload and what's actually coming, and maybe not only do that, but also have some sort of, you train the models in a way to see what's happening for the last so many cycles and maybe thousands of cycles so that you can start actually predicting. So that's kind of the methodology that I think we will move into.
I think so too. It's not clear how long-term this type of predictive activity will be, but I think now it is very important. I completely agree with you. Marcus, what do you think are the main economic drivers of the energy efficiency space?
Yeah, so I'll take a look at this problem in the other different perspective. I think this is because of the limitation of energy locations is different. For example, U.S. is energy-rich countries. We know that. And for the other countries, maybe it's an island like Fiji or something, they are limited by energy. So in other words, for the I'll say energy not rich or poor countries, they have to develop the technologies to perform the similar things that they can do as compared with the US, right? For example, let's take a look at data centers, right? If you have a powerful data center, you can do a rich training and like infinite inferences with support billions users and so on, right? But if you're on an island, Hawaii and so on, they don't have that power data center. So if you want to perform the similar applications, for example, maybe like a drone or robotics, you need a real-time inference and so on. They don't have that capability, right? So in that kind of the gap of supporting the existing or the future application, that's the effect. In fact, the real drivers for moving us to moving forward. So for IEEE's world, right, we want to bring all the technologies to the energy poverty area, including Africa and so on, right? So I think that's the motivations to drive the market to allow everybody to use the same or similar technology around the world.
Thank you very much, Marcus. That's true. It's impossible to disagree with it. Now that we are approaching the last topic and conclusions of our discussion, can I ask you two things? What do you think is the main long-term advance that's needed to make the space successful? And also, are you optimistic that we will achieve notable success in the short term?
Yeah, so I will start with my conclusion first. Right? I'm very optimistic on the technology advancement. So take a look at the LLM or advanced for the AI. We don't have that like 10 years ago, right? So when we measure the futures, we already measures in bring the glasses like I'm wearing right now, right? Measure in the future with the current understanding, which is typically wrong, right? So I'm very optimistic on the future's advancements. We will break these technologies barriers with a new technology. And what is like that, right? I think one of the things I want to bring your attention in my power PMIC management domain is that people are still using the AI workload to shape even though their thermal routing layers inside the chip, right? So we don't have that technology like 10 years ago. Now, if you know the AI workload well, you can distribute the temperature inside your chip and help it to sync it more appropriately and achieve a 10% or 20% increase in the efficiency and so on. And be mindful, roughly 30% of the energy is wasted right into the heat. So, technology like that will help us to bring us to the better future. And the other things I want to stress is that for all researchers around the world, I encourage to join all public events like IEEE, nonprofit organizations. I think together we can build the future better.
Thank you. And it's good considering that energy consumption increases like something 20-30% annually. It's great that you have an optimistic view as well as a specific key area where improvements are now possible. Thank you. Thank you very much. Sean, what is your view? What do you believe will be the most important longer-term advance, and are you optimistic?
Well, maybe just to touch on the first one, there's an interesting one that I think could emerge in the longer term, just to make compute a lot more fundamentally efficient. Is we have been reaching some limits of what we can do with traditional CMOS technology, but there are some researchers looking at other forms of transistor technologies that are actually based on quantum mechanics, like spin-based things, where you're actually changing the spin of a particle rather than moving electrons around. And those can be far more energy efficient. So this is kind of what we would call beyond CMOS technology. And that may still be some time away, but there are, tremendous, fundamental efficiency gains that could be had there if we could do that. And I think, to add, I guess I am less optimistic on how we're going to use all this AI and what the impact is going to be to our culture and society. But if you just talk about the technology, I think we tend to rise to the occasion. And when there's a challenge, there's some technologies that are not always at the forefront. Normally, we worry about performance. As you know, security is not always top of mind, and people aren't always worried to pay for it. AI may be helping to make that more important. Also, energy efficiency and sustainability. I think AI is making that critical right now because they have to build these massive data centers. So we should take advantage of this moment. Innovators that have ideas in grid technologies or these new kind of more efficient workload, carbon aware kind of approaches. Now I think is the time to put forth those ideas, because there's a lot of money flying around and there's people that are looking for any possible solution to power these things. And so that could be solar, that could be wind, that could be ways to get those things integrated. So I think there's, if I take an optimistic viewpoint, I think we may get to a point where we overbuild and we have abundance, but wouldn't it be nice if in the meantime we made a better grid and then everything is better than where we started?
Excellent point. And I share your view that the social impact of artificial intelligence is yet not clear and could be cause for alarm with good justification. But I'm glad that you are optimistic about the technology development. And it is true that the most fundamental, the most obvious things like the grid, for instance, in this case, like faster development of complex systems, like completely new approaches to how we design hardware, what are the principles of design of hardware would be key in this case. And it's good that in this direction you have considerable optimism. Thank you very much. Rahima, what is your view? What do you think is the most important longer term innovation?
Longer term,
are you optimistic?
I'm very optimistic. For longer term innovation, I think some of the things that I really see happening in this decade for sure are three things. One is this, for a long time, I was thinking about microfluidic cooling. And I think there's enough data now to show that you actually have 3x performance improvement. So I think that will become a reality. I think the second one that will become a big reality is we've been working on silicon photonics for the last 20, 25 years.
Right.
I think now slowly, because of this very strong need, and as Sean mentioned, how to take advantage of the time that we are in, the AI era that we are in, this is the time that actually this will see the light at the end of the tunnel. And the third one that I think I touched on is really the expanding on the simulation at scale, but trying to think very carefully about how to use AI for silicon design, for physics intelligence, because now we just have to expand the details expand it to the point where we have all the shortcomings we have, how to utilize it in a different way using AI. So those are my three things. But as far as I'm concerned, I personally think that, very much like Sean, I also believe that this is the fantastic time to really think about sustainability and energy efficiency and grid improvement, mainly because sometimes, at least in the prior years, that did not get the attention that it deserved. Everything in the power grid world is probably 20, 30 years old. Now, because of the kind of problem that we are in, I think we do have the engineering creativity to rise to the occasion as we need it. So we will get there. And I think we have seen many of these inflections, but we are at a very tough inflection now, but we'll get there.
Thank you very much, Rahima. So you are optimistic and you think it's the right time to make real progress where, because of several considerations, it was difficult to make progress before, and that we will improve cooling, achieve simulation at scale, and also make silicon photonics reality in many more fields than it is now. Thank you very much. That certainly makes sense. And Ro, final word. You have the final word. What is the most important, and are you optimistic?
Well, I am optimistic because I'm a strong believer in the capacity of human beings, and that's exactly what we need now. Um, um, as we have heard from the panelists and the panel discussion, we do have the technical tools to improve AI efficiency and make a reality. And we can also act ad hoc, as Rahima was saying, with creativity and things. What I believe is different with respect to other technology, and that's why I'm optimistic, is the human driver behind it, that is not only the driver that comes from technologies or company interests or things like that. And that's just because AI touches basically everyone's life directly. It shapes it, it amplifies it, it can make it a little bit worse, a little bit better, and things. So there is a lot more behind it compared to other technologies that pushes the technology, and the rest is basically is either undergoing, we have a line of sight of it, like new materials, a next generation of scaling, silicon photonics. As some may know, I'm a strong believer of that, and things. So I think we have the technical tools to improve efficiency, and we'll figure it out. So that will happen.
Thank you very much, Ro. I am glad that we concluded on this note of optimism, that it's a good time. It's not an easy time. We have a lot of problems to solve, but it's a good time to address the problems that so far appeared not tractable, but they might be much more solvable now, and there will be both a technical and a social benefit to what we are doing. Thank you very much for taking part in this discussion. Marcus, Sean, Rahima, Roar, thank you very much for sharing your insights. And with that, I send this to David Goodman to conclude this session.
Thank you, Claire, and thank you for
David?
moderating a great discussion. And thank you to all the panelists for showing up and engaging so comprehensively. Always good to finish on a positive note of optimism. And it's also good to hear that we human beings are just about still in control of the whole situation, because the alternative is not attractive. So you got to believe that. Anyway, thank you so much. And the recording will be available in a few days' time, as will the short anonymous report that will be on our Substack account. So with that, have a great day, and I hope to meet you all again.